challenges in optimal design. I'm pleased to introduce Jesus Martinez-Frutos. He'll speak about level set topology optimization for a robust design of structures under internal porosity constraints.
Well, thank you. First of all, I want to thank the organizers for inviting me to this workshop. And I'm going to talk about topology optimization approach that deals with the negative porosity effects that appears in the course of manufacturing process as imperfections. This is a joint work with Grégoire Allaire, Dapogny and Francisco Periago. Well, this is a brief outline of this presentation. Before presenting the proposal, the proposed porosity constraint and numerical result, I'd like to motivate this talk presenting some examples in manufacturing in which this kind of defects appear. Well, basically in topology optimization, we aim at finding an optimal material distribution in a given design domain, which is subjected to some loads, boundary conditions, also possibly constraints, and with the final goal of improving the performance of this structure. And there is also an appealing feature of these topology optimization techniques, that is that these techniques provide an optimal design without depending on designer's a priori knowledge. So this is a very attractive thing that makes this topology optimization technique very popular in industry. So nowadays this field is quite mature, and in the last 20-25 years there has been a great improvement and a lot of successful applications of these techniques in many fields to obtain innovative and high performance designs at the very early stages of the design process. Some examples are, of course, the design of micromaterials, metamaterials, also micro grippers, and also application in industries like automotive industry and aircraft industry. These two industries push it a lot, this kind of topology optimization methods. Well, more recently, there is an increasing interest in incorporating real-life issues in the formulation of topology optimization with the perspective of bridging the gap between the mathematical models with the conceptual designs and some concrete applications. So some examples are those that I'm going to present now. The first one is the introduction of sources of uncertainty in the design. These sources of uncertainties act in all the possible input data of the problem, for instance in loading, also in material properties. In this example we have random modeling of the heat conductivity, and also in geometry. Notice that for geometry this optimal design after fabrication can break in these regions which are very thin regions, so there are some tolerances in manufacturing that can cause the breaks of these kind of things. Well, another very prolific research field that tomorrow we will have a nice presentation is the introduction of manufacturing constraints. So I don't want to present an exhaustive review here, just to mention some of them, some works that has to do with the porosity constraint indirectly. The first one is the introduction of geometrical constraints. For instance, the minimal thickness and maximal thickness. We'll see that this constraint, the maximal thickness, has to do with one of the very important defects that we find in casting, which is the shrinkage cavities. Another manufacturing constraint is casting constraint for moldability. And of course, Monday we saw a presentation about overhang limitations for reducing the material devoted for the support of the structures in 3D printing. Well, more recently there are also some improvements to take into account the thermal residual stresses and also deformations that can be produced during processes like selective laser melting. Well, this presentation is devoted to address the negative effects of porosity. What is porosity? Well, porosity is the parasitic emergence of small bubbles of air inside the material that occurs during the manufacturing constraint, during the manufacturing process, sorry. So for those that are not quite familiar with these kind of defects, I'm going to present some examples in which we can find these porosity defects. The first one is manufacturing, casting manufacturing. In casting manufacturing, we want a metal to cast into a shape, and this is done by melting it, then putting it into a mold, and then removing the mold material when this metal has solidified. So in this process appears lots of issues. Most of them are related with the different properties that has the liquid, the metal in liquid state and in solid state. So one of them is the different capacity that has the material in liquid state to dissolve gases. So during the process of cooling, these gases get trapped inside the material and lead to this kind of defect, which are known pinholes, and are very tiny holes very close to the surface, and we will see that are very related with failure due to fatigue. And also we can find other kind of holes which are larger cavities that we can find then inside the domain. So these two examples of real situations in which we have these two defects. Another important defect that we find in casting manufacturing is the shrinkage cavities. The shrinkage cavities are cavities that appears due to the different density that has the metal in liquid state and in solid state. So during the cooling process, the metal retracts a little and gets more dense, so leaving in the hot spots of the structure without any material. So this defect is very harmful because it's related with fracture and other kind of degradations of the performance of the structure. Here we have some relation between this porosity defect and the mechanical and fracture performance of the final casting. So there are some reference. One of them is this one by Harding that studied this effect of porosity on the deformation, damage and fracture of cast steel, and basically is divided in, it depends on the size of the holes. So for macroscopic porosity, this macroscopic porosity introduces a redistribution of the stress inside the solid, and also there are a stress concentration around the micropores. So this can cause micro cracks and failure. Also, this size of the holes are related with the degradation in the elastic modulus, fracture energy, and fracture toughness. So microporosity is related with failure of fracture. On the other hand, we have microporosity. This microporosity does not result in a loss of stiffness or stress redistribution, but greatly affect fatigue and ductility. So those are some of the consequences of having these kind of defects inside the structures. Well, apart of casting manufacturing, porosity also appears in other manufacturing processes like welding. In welding, when the weld pool is melt, there are some gases that get trapped as it solidifies. So we have this kind of defects that are small holes, and also we have another kind of defects like incomplete penetration, root crack, and lack of fusion that also can be treated with the formulation I'm going to propose later on. When of course in the new additive manufacturing processes we have porosity. This porosity can be reduced a little bit by controlling the processes to produce the powders for the 3D printing, but we cannot eliminate them 100%. So it's required to develop new techniques that makes the final structure more robust against this kind of defects. Well, apart of the metal, finally, we have another materials which are porous. very commonly used in civil engineering and also in architecture, which is, for example, concrete. Concrete is a composite material which is composed of water, cement, some small stones, and when this water evaporates, leave behind a network of capillarity pores in the concrete, which are very, very related with the strength of this material. Well, so we have seen that this porosity affects in a great deal the reliability and quality of these materials. So we need to develop new techniques to take this porosity into account in the design process. So the objective of this talk is to introduce an approach that provides optimal shape against the emergence of these small holes in the course of the manufacturing process. So there, in the literature, there are some other works that does not consider explicitly the porosity in the formulation, but introduce other kinds of manufacturing constraints that can address implicitly this kind of defects. Some of them are this work that introduce casting constraint in geometry, thickness, and there are other works that introduce constraint in the cooling process. So the cooling process is very related with the shrinkage cavities. So controlling this process indirectly facilitates the reduction of the porosity effects. Well, so the problem is shape and topology optimization. So when we want to minimize some function, we need to choose an objective function J. So the problem is to find a subdomain capital omega which is contained on a set of admissible shapes that contain the Dirichlet region and the Neumann region, and also a volume constraint. And these minimization problems also could have some constraints. The porosity constraint we are going to see later on. And this objective functional and constraint has this form. We have an integrand which depends on a state variable, which is the solution of a PD. In our case, this PD is the linear elasticity, but we could have here other more complicated PDs involving contacts or couple problems. Well, this shape and topology optimization problem is going to be solved using level set method, originally used by Osher and Setian in the context of fluid mechanics, and then extended by Allaire and Wan in the context of shape optimization. So basically in level set method, we have a parametrization of the shape with a level set function that takes values, negative values inside the domain, positive values outside the domain, and it's equal to 0 in the boundary. So this level set function exists in all the points of the domain and also depends on a pseudo time tau. This level set function, we want to evolve it. So the only thing that matters here is the normal velocity of to the boundary. This normal velocity is v, and this evolution, the behavior is given by the solution of this Hamilton-Jacobi equation. So the key here is to know what is this normal velocity. This normal velocity is not a physical velocity, but a pseudo velocity that is related with the optimization problem. So it's related most with the computational, with the gradient computation, and in particular with the shape gradient computation. So there is a method for computing the shape gradient that goes back to Hadamard and consists of parameterizing the variations of the shape with a vector field theta, so that every point x in the boundary has goes to a new point theta of x in the variation of the boundary. So skipping some of the details, there is a theorem which is called Hadamard structure theorem that gives you the shape derivative whatever the function you want to differentiate is. So this shape derivatives is given by the integral in the boundary of the normal component of this vector field theta times an integral a function v This function depends on the state equation and a joint equation. So basically this is some basically notions of the shape derivatives. Well, with this shape derivative, what we need to do is what is this velocity here. So we can choose, we can make this choice and taking theta as the product between v and n, and take it the negative to have a negative derivative, and we see that we have a descent direction, and we can infer from here that the normal velocity is minus v. Well, once I have introduced a little bit the problem, I'm going to show you some of the constraints we have developed to take into account porosity. So the main objective here is to obtain shapes which are optimal with respect to one structural performance, but at the same time are robust to against the emergence of small holes inside the domain. So imagine a domain capital omega in which we have a point x. In this point x, we create an infinitesimal hole with a radius rho. So the domain, the perforated domain, is this one, is capital omega x rho. So this objective, this requirement is given by this expression. This expression tells us that the functional evaluated in the original domain cannot be degraded more than a certain percentage eta when it is evaluated in the perforated domain, right? So this expression we need to transform in an inequality constraint. So we are going to approximate this term here using an asymptotical, topological asymptotical expansion and the topological derivative. So this kind of asymptotical expansion are commonly used in many fields, and in particular in shape and topology optimization. In this field, in shape and topology optimization, this topological derivative is used to nucleate holes and to remove material inside the domain. So we are going to use this topological derivative in a slightly different way, because we are using to approximate the functional in the perforated domain. So this expansion can be shown here. We have the objective the functional evaluated in the perforated domain equal to the functional in the original domain, plus a function that depends on the radius, the size of the perturbation, elevated to d. This is the dimension of the problem, and this is the topological derivative. There is a reminder that we need to guarantee that vanishes faster than this function. So this topological derivative represents the variation of the shape functional when the domain is perturbed by just one infinitesimal hole. Well, using this expression, we can replace this initial requirement by this other one. This other one, up to the leading order of rho, can lead us to this pointwise constraint that holds for any point in the domain capital omega. So this pointwise constraint can be transformed in an integral constraint like this. So this is going to be our porosity constraint in the formulation. So there are some remarks I'd like to mention here. The first one is that in the asymptotic expansion, we assume that we just create a single hole, a single infinitesimal hole. But in real cases, we have a lot of many holes. So if we repeat all the derivation I presented before, taking into account that small omega is the union of a set of many holes, okay, at different positions, this constraint here can take into account the effect of all of them. The second remark is most related with a possibility of improvement, which is related with the shrinkage defects. So we can also, in this constraint, we can include a weight on the distance function to the boundary. Why? Because the shrinkage cavities appears in hot spots of the structures and are even more probably to appear when there are a large thickness, parts with large thickness. So we can extend this previous work to incorporate this weight on the distance function to the boundary in the formulation. The third remark about the porosity constraint is related with the defects in the boundary, because we assume that in topological gradient the hole is inside the boundary. So what about if we have a defect in the boundary? So we have two possibilities. One of them is to consider the topological asymptotic with respect to a singular boundary perturbation that we can find in this paper, and another choice is to model the problem as an optimization under uncertainty problem, in which we have a random field that model the perturbation of the boundary. So we could introduce this random field in the vector field theta to consider variations of the boundary. So our safe optimization problem is this one. In this problem, we have the porosity constraint that acts in one functional that does not have to be the same that the one that we are minimizing. So we can minimize the compliance and impose a porosity constraint on the stress, for instance. So in this presentation, I'm going to show you some results when we use the porosity constraint for compliance and this porosity constraint for stress. So let's look how the shape derivatives looks like for these two porosity constraints. The first one is the compliance. So for the case of compliance, it's well known that the problem is self-adjoint and we have this shape derivative. And in the case of the porosity constraint, we have this topological derivative of the compliant that has this form that depends on three scalar values containing the Lamé coefficient. And if we take the shape derivative of this porosity constraint, we obtain something like this with three terms that are integral in the boundary, in the free boundary, and an adjoint p omega emerges due to the state equation that we impose in the Lagrangian during the calculation of shape derivative. So this p omega, this adjoint state, is the solution of this PDE in variational form that is quite similar to the linear elasticity system, but with a different right-hand side that includes the partial derivative of the topological gradient with respect to u. So we are doing here the shape derivative of the topological derivative. Well, in the case of stress, we have a little bit more complicated shape derivative. So the shape derivative for the stress for a functional j that depends on the stress is a generic functional is given by this formula, and this p is an adjoint state which solves this problem in variational form. So in this problem we have here A, which is the hook tensor that applies to j prime, which is the partial derivative of j with respect to the stress tensor. So this is the shape derivative for this functional, and for the case of the porosity constraint for stress, we limit ourselves to the case of 2D, and we are going to use this functional of the stress. This is a localization parameter, and this is the only case in which we have a topological derivative. So this topological derivative is given by this expression in which we have this p omega, which is the solution of the same problem that I explained here. So for this case, the shape derivative of this porosity constraint is something like this, in which we have 4 terms. We have the adjoint p, and we have another 2 adjoints which are theta and q. So these two adjoints comes from the introduction of the state equation and from the introduction of this adjoint equation in the Lagrangian. So theta is the solution of this problem, which is related with the state equation, and q is the solution of the other problem here. So once we have this information about safe derivatives, we incorporate them into an augmented Lagrangian functional, and we have something like this, in which we have some Lagrangian multipliers and also penalty factors that are going to be updated during the optimization. And the shape derivative of this Lagrangian contains also the shape derivative that we have just computed for the functionals and for the constraints. So this is a sketch of the algorithm. So after an initial guess, we compute the adjoint the state equation, the displacement field, and at a domain capital omega in the iteration n. Then we will compute the shape derivative of the Lagrangian, and from them we can infer this normal velocity, looking at the terms that multiplies the normal component of this vector field theta. So once we have this normal velocity, we can solve the Hamilton-Jacobi equation and evolve the shape to the next step. So now I'm going to show you some numerical results. We solved two different problems. The first one is a problem that minimizes the compliance for obtaining a maximal stiffness for the structure, and the second one is devoted for the design of compliant mechanism. So in both cases, we are going to solve the problem with the porosity constraint in compliance and also the porosity constraint in the stress in both cases. So let's start with the first experiment about the minimum structural compliance. Is this L-shaped beam, which is clamped in the upper side, and there is also a force downwards in the right-hand side of the domain. And this is the initial guess. And there is a constraint in the volume, which is the 35% of the initial volume. So here I have to say something about the numerical implementation, which is that first we solve the problem without any porosity constraint and obtain an optimal design. This optimal design is going to be the initial guess of a second stage in which we are going to impose the porosity constraint. Why we did this in this two-stage approach? Because trying to imposing this difficult porosity constraint for the intricate designs that we obtain at the first iterations of the optimization lead to a local minimum with a very, very poor performance from the structural point of view. So we start from this initial guess to obtain an optimal design that minimizes also the porosity. So this is the evolution of the compliance and the porosity constraint for the first case, and we see here that we just have 15 iterations that are accumulated after all the iterations that we needed to obtain this design. So once we obtain this design, after 15 iterations, we have a reduction in the porosity constraint from this number to this number. So we have a great reduction in the porosity constraint that is achieved at the cost of degrading the compliance. The compliance is increased by 6.5%, right? So these results were achieved with this configuration, with the value of eta equal to 0.01 and the size of the porosity rho equal to 0.625, which is the size of one cell of the mesh. You can choose, of course, other sizes for this rho, but remember that we have a parameter eta rho in the constraint. Let me go back. here, this theta rho is the only thing that matters numerically, from the numerical point of view. So, well, this is the two designs that we obtained. On the left-hand side, we have the design that we obtained without the porosity constraint, and on the right-hand side, we have the design that we obtained introducing this porosity constraint. So the effect is that the reentrant corner is smooth and rounded in this case, and the peak value of this field here is reduced a great deal. So this field here is the integrand of the porosity constraint, is this quantity. Is this quantity here. So we can also reduce this parameter eta to give the porosity more importance in the design, and we have this result. In this result, we see that the regions that are sensitive to the porosity are larger, and as a consequence, we have also a larger radio of this corner compared to the previous one. And also we see that we have this reduction in the peak value again. Well, this modification of the shape can be shown in detail if we overlapped the design without the porosity constraint and the design without the porosity constraint and with the porosity constraint. We see that we have a smooth of this sharp region, and also these regions that connects more than 3 bars are larger and more rounded, whereas in the previous one, just the modification of the shape is more local in this corner. So let's see what happens when we introduce the porosity constraint in stress. In this case, we have similar changes in the shape in the optimal shape. We see that the peak value is reduced a great deal also, and this topological optimal shape seems to be the same as this one. Is very, very similar, but we will see later on when we analyze in fracture that it has slightly differences. So when we introduce this porosity constraint in stress, we also have some extra benefits, which are that the stress field, the stress level in the structure is also reduced from 11 to the peak stress from 11 to 1.3, and now what we want to do is to analyze all these designs against fracture. So to do that, before analyzing this design, I want to introduce some notation about the simulation we are going to do. So we are using a phase field method. What the phase field method does basically is to smooth a sharp cracked surface by introducing a parameter S, which is the phase field parameter, and also an L0 parameter, which is a length scale parameter. So as customary in phase field method, we have two PDEs which are coupled. The first PDE is related with the mechanical problem, and the second PDE is related with the evolution of this parameter S, with this phase field parameter. So in this PDE, it's quite similar to the elasticity system, but we have a degradation function J that apply to the stress tensor. In the second PDE, we have J prime, which is the driving force, psi E is the elastic energy, and JC is the fracture toughness. So we solve this couple problem in a staggered way. So, in particular, we are going to use 100 iterations, load steps, and those are the results of this simulation. Here you can see that the first design that start fracturing is the design with no constraint that start fracturing in the iteration 55 or 60 more or less. Then the other designs that fracture in these numerical experiments are the design with the compliant constraint, the porosity constraint in compliance with these two values of eta. So notice that for this value of eta, the design has broken a bar, and in this design the fracture just has initiated. In the case of a stress constraint, we don't have a fracture for this load. Well, these conclusions can be seen if we represent the force versus the displacement. So we see here that for the design that we obtain without the porosity constraint, we have a fracture here, and there is a remain stiffness in the design because the design also have, after this fracture, still have some stiffness, so the curve cannot get to zero, so it stay here. And next we have a fracture for the blue curve and for the green. So these two are the two designs that take into account the porosity constraint for compliance. So in the second example, I like to show you some 3D effects that appear in when we introduce this formulation in a 3D example. So we want to analyze the impact that porosity constraint has in the design in 3D, and it is expected that this impact is in regions with very small features. So we need to mesh this domain with a high resolution mesh. So we use 2.5 million of elements that give us around 8 million of degrees of freedom, and also we are going to use a very small volume constraint in order to have these very small feature sizes. And this is the design that we obtain first without imposing the porosity constraint, and taking this design as an initial guess, we have this other design. So if we compare both, the peak value is also reduced 3 orders of magnitude, and we see that what this porosity constraint does is to eliminate thin bars of the structure, and also to round the corner to smooth sharp regions. But there are other effects that, if we zoom here, we can see that in the out of plane direction, the surface of this corner is inflated. So we have also a 3D effect when we solve the problem with these porosity constraints. Well, let's see now the second experiment. The second experiment is devoted to the design of compliant mechanism. So we maximize objective functional that depends on the displacement, and in particular is this objective functional here. So we are going to solve this problem, which is the inverter mechanism, that consists in maximizing the horizontal displacement in the output region, and at the same time minimizing the input displacement in the region that we are going to introduce a Neumann condition. So this is the objective function that we introduce that combines these two displacements, and they have a weight, each of one. The horizontal displacement for the input has a weight of 1, and the horizontal displacement for the output has a weight of 2. So the optimal shape that we obtain without imposing this porosity constraint is this one. And if we impose a porosity constraint in compliance, we see that we have a reduction to 0 of the constraint, but at the cost of increasing this functional by a 33%. So this is something that we could expect, because we are trying to maximize a functional related with the flexibility of the mechanism, but introduce a porosity constraint in the compliance, which has to do with the stiffness. So we have something like a multi-criteria problem that, of course, this multi-objective problem, we can control it by modifying the parameter eta. This parameter eta in porosity. We see that these results correspond to these two designs, and here we can clearly see that we can eliminate the porosity that appear in regions which are close to be hinges, are very weak regions, and these regions are increasing thickness to eliminate this porosity sensitivity. The consequence is that the output displacement is not as high as the displacement that we had with the design without this porosity constraint. So this is a small drawback of this problem, but we can control it by modifying this parameter. So if we take here a value, a greater value, we can be more closer to the mechanism and less closer to the structure. So if we decrease this value, we will have something like this, which is more closer to a structure than a mechanism. So the effect is that this part increases in thickness a lot. Well, in the case of stress, we have similar conclusions from the I presented before, and we have this design that is quite similar. If you see, this is quite similar to this other one for compliance, and also have a reduction in the stress level of the structure that is reduced 1 order of magnitude in this case. Well, so finally, after this numerical example, I'd like to talk about some conclusions and possible works of this formulation. The first conclusion is that we achieve the main goal that I presented before, that is alleviating the impact of the parasitic emergence of small bubbles of air inside the domain during the manufacturing process. So this is the main objective that we obtain with this formulation. Also, with respect to the optimal design of the structure, what this formulation does is to remove thin bars and smooth subregions of the shape. Also, at a side effect, reduces the stress level and provides a higher load carrying capacity prior to fracture. So the designs are not optimal for fracture, but have a better behavior against fracture. For the case of this optimal design of mechanisms, the conclusions are that the weak regions that are prone to create hinges are reinforced, and also there is a reduction of the stress level of the mechanism. So in the experiment I performed, there is a reduction of the influence of this porosity at the cost of degrading the objective function, which reveals some kind of multi-criteria nature of the problem, but can be controlled by tuning this parameter, eta. And finally, there are some other conclusions related with the computational efficiency of the method, because we can understand this method also as a post-processing stage of the traditional shape optimization, because with very low number of iterations we can improve the design in terms of stress and also in terms of fracture. And also we have taken into account porosity, but using a macroscopic approach. So another advantage of this approach is that it's valid for different manufacturing processes and also different materials, because we have not particularized for any kind of manufacturing process. But it's general, but at the same time has the flexibility to fit these two parameters to a specifically manufacturing process. So as a future work, we could extend to the case where the small grains of another material are included inside a bulk phase. So with this extension, considering the topological derivative of an inclusion, we can address problems like the slag inclusion in casting and also solid inclusions in welding, like this one. Another example is another future work is to consider other kinds of shapes For the porosity, we have considered porosity that are circle or spheres, but we can consider anisotropic holes that could be interesting to study for example, microcracks like this one. Also, as I said, we can feed this parameter to experimental data as well, and there are also some ongoing works devoting to including explicitly the fracture and the fatigue phenomenon inside the formulation, because in these experiments I presented before, we have an improvement in fracture, but the design is not the optimal for fracture because it's not including the formulation. So one possible improvement is to include this fracture inside the topology optimization formulation. So finally, you can find more details about the shape derivatives and some proofs in this paper we just published, and that's all that I want to talk to you today. Thank you.
Thank you very much. Questions? Yes.
Maybe I missed something, but in your when you build your cost function, you have a quadratic penalization of your porosity constraint. Can you maybe it was maybe in the beginning when you build your cost, once you have the topological derivative, you have some was the integral of
Here?
No. After
here.
Yes, it's squared.
Yes.
So you cannot guarantee that you fulfill some constraint.
If this constraint this holds in any point, so if you take this norm, you can transform it into this other one, this integral form, and if this is 0, this is the positive part.
There's a little plus down there.
This is
yes, I see. But
so
since you have a square, I mean, did you try another power?
no.
But would it be useful? Or?
I don't know. It's the I didn't try any other because it indeed is the constraint is fulfilled because I checked in the results, in the final result. So I didn't think about introducing another exponent.
Surprising is fulfilled with the square.
But it is.
Yeah, okay.
At least for this example, but maybe it's not. You are right.
Okay, so there was a question. Yes. Back there. Go ahead, please. Yeah.
Yeah, so now the size of your hole is dependent on an element in the mesh, right?
Yes.
Did you do some convergence studies where you
No.
sort of increase your... Okay.
No, I just I just take the smallest element as the radius of the porosity.
I would just be interested
But
if you take twice a finer mesh and then take a hole which is 2 elements, or do you see the same result?
I don't expect the shape to change because are quite similar in when we change this porosity constraint in compliance and we change to stress, the effect is quite similar. So I don't expect that refining the mesh to obtain something different in this example, because this example is the problem is very local here. So although you refine the mesh, you still have the problem in the same place, so you will have the same effect.
Yes, Michael.
It nicely combines topological derivative and these pores, but that assumes that the pores are quite isolated. In this application of these shrinkage cavities, we have lining up pores, and they strongly interact. So how does this conflict with the...
I know what you mean. You are right, but at this moment I don't came up with a way to take this into account, because it's based on topological gradient, which basically is an infinitesimal hole, And you have seen that these kind of defects, like a shrinkage, are not infinitesimal, so and are very close. So each one affects the other, and there are some complicated effects there that I think this is difficult to model in a macroscopic way. So that we did.
Felix?
So you mentioned at the end of your talk that it would be interesting to consider anisotropic holes, but I mean, wouldn't it even be kind of natural to, right from the beginning, if you're interested in cracks, to consider a codimension 1 kind of little discs, and in which case it's not just the position of the disc but also the normal of the disc.
The direction is even more important.
In the shape derivative. I mean, from the theory of crack propagation, that looks natural to me.
Of course.
Have people done
Yeah,
that?
of course.
Is that being done? I mean, having a kind of a topological derivative
Yes.
which takes into account
I don't know.
infinitesimal disks, that has been
Well,
done.
not in this context, but people interested in doing a topological derivative to know where it will nucleate a fracture. So Sokolowski and some co-workers.
Further questions? I have
First part.
two very short questions. One is, in the old days, people used to think that one should try to relax these problems and do absolute energy minimization or compliance minimization or so forth. And your method is to introduce, at the beginning of your talk, was to introduce infinitesimal holes and define a shape derivative. Of course, you could have, it could be at some stage in the iteration, it's best to introduce a finite size hole or maybe two finite size holes.
Yes.
Whereas that might not be picked up by the shape derivative of an infinitesimal hole.
Yeah.
These were issues that people discussed many years ago. I guess Grégoire would remember this. So, is there a relaxation approach to these kind of problems, or is there a reason not to consider those approaches?
To my best knowledge, I don't know.
Okay, yeah.
But-
Second question is on slide 51. I don't completely understand the objective function, but it almost looks like this point on the right wants to be, you want to have a large motion of that point on the right, and the point on the left, you want to have a small motion with a applied force.
Yes.
So it's like a little actuator.
Yes, yeah.
And then you find out these points with that have the porosity.
The hinges.
Yeah, and the singular points, and it looks very natural that at those points, that you should then put a hinge at those points.
Yeah.
The method doesn't really allow you, I guess, to put a hinge there, but
Yeah.
maybe one should
Because
have
it's
methods
a
that
conflicting.
allow hinges somehow to appear. Maybe you need a shape derivative for hinges or something. But
yeah.
I believe if you put hinges where those red marks are, it could be even better somehow. You'd have to allow sliding of material if you have a hinge.
Yeah, in these cases, you need these kind of hinges to get this motion, but maybe if you introduce some kind of hyperelastic material, you can get this displacement with large deformation without having these kind of things. But with this kind of material, of course, you need these hinges to obtain the displacement.
But I'm thinking in terms of an actual hinge where the material, naturally in the optimization, you end up with something like this.
Yeah, but
sliding
you need to know a priori where the hinge is. That's a problem.
Yeah.
But to go on your comment, the typical application here is micromechanism.
Yeah,
that
right,
you will,
okay.
etch in silicium or whatever. So at a very small
Right.
scale, you don't want to use inch.
Okay. Yeah.
Okay, but that's an academic test kit now.
Very good. Further questions? Okay, let's thank Jesus again.
Okay, thank you.